Hi, and welcome back to my videos for General Chemistry 2. Today, we'll see how we can do calculations with one of the most abstract properties of atoms and molecules, the entropy. We'll also start to understand how entropy makes endothermic reactions possible even though they give rise to products with a higher potential energy than the reactants. To begin, let's talk a little bit more about the entropy. You might recall that one way we can think about entropy is that it's a way of measuring the disorder or randomness in a system. But how can we determine an exact number for the degree of randomness? Well, at the end of the last video, we saw that the third law of thermodynamics states that the entropy of a perfect crystal is zero when the temperature is absolute zero. It turns out that this gives us a way to determine the exact entropy of any substance. To find the entropy of a compound, for example liquid water, we just need to determine how disordered it is compared to a perfect crystal. Unfortunately, that is not easy to do, but luckily for us, this has already been done over the years, and as a result, there's a long list of entropies in the third column of Appendix C in your textbook. The symbol for entropy is a capital letter S, and it has units of joules over kelvins times moles. Notice that, unlike the enthalpy, the units for entropy include kelvins. If you think about it, that makes sense. We know that the temperature has a big effect on the entropy. The higher the temperature, the more disordered a system becomes. So, the temperature affects the entropy quite a lot. You can actually see that in the data in Appendix C. Notice that the entropy in Appendix C has the symbol S with a little circle next to it. We usually call that symbol S0. The little circle means that the data was measured at standard temperature and pressure. That means 25 degrees Celsius and 1 atmosphere. If we do an experiment at any other temperature, the entropy will be different. We'll see exactly how the temperature changes the entropy in the next video. But for now, we'll just work on the problems where the temperature is at 25 Celsius. So, what can we do with the entropy data in Appendix C? Well, from General Chem 1, you might remember that we can also use Appendix C to calculate the enthalpy change that happens during a reaction. Here's the equation that we used for that. The enthalpy change for a reaction is just the enthalpy of the products minus the enthalpy of the reactants. It turns out that we can find the entropy change in a very similar way. For example, consider this reaction. If we want to know its entropy, we just look up the entropies of the products and reactants in Appendix C and plug them into the equation. The entropy of magnesium hydroxide is 63.24 joules per Kelvin mole. Magnesium oxide is 28.8, and liquid water is 69.95. Notice that some compounds, including water, appear in the appendix more than once. That's because the entropy is different depending on whether the compound is a gas, a liquid, or a solid. If more than one phase is listed, be careful to use the data for the phase that you really want. Anyway, when we solve this equation, we find that the entropy change for the reaction is negative 33.51 joules per Kelvin mole. Notice that the entropy is a negative number. That means that the amount of disorder is decreasing. That makes a lot of sense. If you look at the reaction, we started with 2 compounds and ended with just 1. As a result, we'd expect the amount of disorder to decrease. Also, notice that we started with a solid and a liquid, and we ended with just a solid. That's another reason we'd expect the disorder to decrease. And that's exactly what we got from our calculation. Let's try another example. What will be the entropy change for this reaction? Once again, we'll use this formula to determine the entropy of the reaction. The product is water vapor, which has an entropy of 188.83 joules per Kelvin mole. But wait, before we move on, notice that the balanced reaction tells us that we have 2 moles of water vapor, so we'll need to multiply the entropy by 2. Next, we subtract the reactants. Here again, notice that the hydrogen gas has a coefficient of 2, so we'll multiply the entropy of the hydrogen by 2. When we solve the equation, we get negative 88.5 joules per Kelvin. Notice that the units of our answer are joules per Kelvin this time, and not joules per Kelvin mole. That's because we had to multiply some of our data by a coefficient, which has the unit of moles. The oxygen also had a coefficient, but that coefficient was 1, which we didn't write down. But that means that the moles cancel from all of our units. Once again, we got a negative number for the overall entropy. That means the amount of disorder is decreasing. And if you look at the balanced reaction, you'll see why. We started the reaction with 2 different compounds, but ended up with only 1. Let's try one more example. This time, I'll choose a reaction that'll give us an unexpected result. We start with aqueous silver nitrate and sodium chloride as our reactants, and these produce products of solid silver chloride and aqueous sodium nitrate. Since we start with 2 aqueous solutions, but produce a solid, we might predict that the entropy decreases. And that's correct. When we plug in data from Appendix C, we find out that the entropy change is negative 34.32 joules per Kelvin mole. But wait, the second law of thermodynamics tells us that the entropy should always increase during a spontaneous reaction, but the entropy in this example decreased. Are we breaking the second law of thermodynamics? To understand why this reaction can still happen, we just need to remember the details of what the second law actually says. The second law states, a spontaneous process always results in an increase in the entropy of a closed system. The key here is those last 4 words. It turns out that the beaker where this reaction takes place is not a closed system. But why not? The system in this example is more than just the beaker and the chemicals in it. Instead, the system includes both the reaction and its environment. The environment includes the solvent in the beaker, the air in the lab, the glass of the beaker, and so on. The second law says that it's the entropy of the whole system that must increase. So, if the entropy of the reaction goes down, that means the entropy of the environment must go up even more. So, when this reaction occurs, the entropy of the environment must increase. What could make that happen? Well, as you might remember from our discussion of entropy in the last video, one way to increase the entropy is to raise the temperature. So, in order for this reaction to occur, it needs to heat up the environment. So how can we tell if the reaction actually does give off heat? Simple. We just use Appendix C to calculate the enthalpy of the reaction. Remember, this time we look up the enthalpy in the appendix, which is in the first column. When we do, we get this equation. That gives us an enthalpy of negative 65.9 kilojoules per mole. Notice that this is a negative number, so that means this is an exothermic reaction. So the reaction does release heat, which is what makes it possible for the reaction to occur, even though the entropy decreases. Well, that's enough new material for now. Now that we know a little bit about entropy, we're ready to tie the entropy and enthalpy together and see how they're related. That'll allow us to figure out whether or not any chemical reaction is possible. We'll do that in the next video, so I hope you'll join me for that. In the meantime, have a good week.